Before we jump into the representation extension problem, we will first have a brief look at the recognition and the construction problem. We will again make use of ST graphs. So recall those are directed planar graphs with exactly one source and exactly one sink. And we have an embedding where the source and the sink are on the outer face. We also already learned that for ST graphs we can get an ST ordering. For example, by doing a topological sort on this directed acyclic graph. Now the observation is that our orientations we get from ST graphs correspond already to epsilon bar visibility representations. An ST orientation is basically an embedding, so for all the edges we know in which order around the vertices they appear. And if we take the ST order as the y-coordinate and also look at the embedding, then we can immediately construct an epsilon bar visibility representation. So let's try to do that here. We start with 1 at the bottom and 14 at the top, and we have 1 visibility between them. Now we go bottom up. We go according to this order. For number 1, we have 2 neighbors, 2 and 10. We have 2 to the left, so we place it here, but we leave space for number 10 here. Number 2 has 1 outgoing edge to number 3, so we have to place it exactly above. Here we have 4 on the right, so we need some space on the left. We have neighbor 5 on the left, but we need space on the right for neighbor 9. We have 6 on the right, and number 7 spans both the 5 and the 6, so we place it here. Now 8 spans 3 and 7, so we place it from the left point 3 to the right point of 7. Same way we place 9 from 8 to 4. And we do the same thing on the right. We left some space for 10, so we place it here. We have 2 neighbors 11 and 12, so we place them next to each other. And we place number 13 above. And then of course we still have these 2 visibilities here. So if we have an ST graph, then it's quite easy to get such a representation. On the other hand, if we only have a directed acyclic graph, then it's MP hard to recognize whether it has a weak bar visibility representation. Because this question is equivalent to asking whether it has an upward planar drawing. And that we learned earlier is MP complete. But for epsilon bar visibility, we can do a simple test. If we have a directed graph, then we can add a supersource connected to all sources and a supersink connected to all sinks. And if that gives us an ST graph, then we can use this algorithm to draw it. And it has also been shown if that doesn't give us an ST graph, then there is no drawing. So the problem boils down to, can we recognize ST graphs? And that we can do in linear time. For strong bar visibility recognition, on the other case, it's still open. We don't know if we can do it for planar digraphs. So following from this, to draw a directed graph, we first make an ST graph out of it, draw that, and then remove the supersource and the supersink. If we have such a drawing, then it has the following property. It is rectangular. So the representation of the source and of the sink span an enclosing rectangle of the whole thing. That means for the recognition, if we have an ST graph, asking whether there is a rectangular bar visibility representation or whether there is some bar visibility representation is basically equivalent. But for the representation extension problem, it does make a difference. I will present you 3 theorems, 2 of which we will show in the lecture. The first one is rectangular epsilon bar visibility representation extension can be solved in order of n log squared n time for ST graphs. For this theorem, they gave a dynamic program which uses so-called SPQR trees. We won't go so much into the running time. Instead, we will represent an easier version where we get quadratic runtime. To get it down to here, it's quite tough, so we won't have a look at that. It's more interesting for us that we can do it efficiently. The second theorem that we'll prove is, in general case where we're not rectangular, is NP-complete. And for that we will reduce from planar monotone 3 set. Chaplik et al. Also showed that it's NP-complete if the drawing is restricted to the integer grid. This is by reduction from 3 partition. But we will not show this result here.